All right.
Alright, hello everyone, we are officially live for SARP's unveiling of our 2019 to 2021 rocket Pacific Impulse. Thank you all for tuning in. My name is Christina, I am the project manager for SARP this year, and we are so excited to be presenting our system this year, and so excited to have all of you. So just a first thing before we begin, I would like to urge all of you to log into your YouTube accounts or Gmail accounts through YouTube and interact with our live chat because that is going right now, and just show your excitement, show your support for SARP. So I will just go ahead and get into it. So for our overall agenda today, we will be going through a system/team overview, both going a little bit over our competition and our team structure for those of y'all that haven't heard of it before, as well as going into our 2020 to 2021 accomplishments this year. And we will be going through sub-team updates from each of our sub-team leads and going through our accomplishments from the year. So we will be going through our 4 technical sub-team structures: Avionics, Propulsion, and Payload, as well as our business sub-team. And then we will also be officially unveiling our rocket today. And then we will also be going through some updates on the future of our SARP and planning for the next few years. As well as some Q&A and discussion will be opened in a Zoom room afterwards. But yeah, we'll get into it. So for our overall team structure, for those of you that haven't sort of heard of our overall structure before, so we have 2 main administrative leads, me being the project manager along with Kat, sort of maintaining, Kat, the chief engineer, overseeing more of the technical integration side of things. And then we have 4 technical sub-teams, that being Avionics, Payload, Propulsion, and Structures, and then a business lead. As well as a new position that we've had this year is a secretary, the amazing Anna Yates, but we'll go into a little bit go into it in a little bit. And then under each sub-team lead, there is a project lead. There are project leads that oversee the development of subsystems, and then with each project lead, they lead several project members to complete the development of that system. And then going into our leadership team for this year, I've had the amazing honor of working alongside these awesome people, so I'll just go ahead and introduce them. We have Kat Hannes being the chief engineer this year, me being the project manager, and Josh Sherbrooke being the avionics lead, Oliver Rowe the propulsion lead, and Zach Gomi the structures lead, as well as Akash Kurse the payload lead, and Felicia Yan being the business lead, and our new administrative lead, Anna Yates, being the secretary this year. So going into a little bit of an overview of our competition, we are changing over competitions this year to the $1 per foot challenge, and that is hosted by the Friends of Amateur Rocketry, so a different organization, and the SARP team is intending on currently launching in the fall of 2021. So that is a little bit different from our initial plan, but we'll be going into like updates and accomplishments from this year and our current goals for the future. And then also, the competition is located in the Mojave Desert, and a nearby town of like, sort of, a nearby town of that you can Google is Cancel, California. And then an interesting thing about this challenge is that we get awarded $1 per foot of altitude that we attain above the launch rail. So it's going to be an exciting new challenge that SARP is pursuing, and a new step forward for us. And with that, I will be introducing the amazing Kat Hannes, our chief engineer, to go through the overview.
All right. Hi, everybody. As Christina said, my name is Kat Hannes, and I've had the absolute honor of serving as SARP's chief engineer this past school year. So a quick overview about our rocket. Our rocket's name is Pacific Impulse, and this is SARP's first ever bipropellant rocket. This means that we use liquid oxidizer and a liquid fuel. So for our propulsive system, we have a single stage rocket, and it's actually pressure fed. So our fuel is an ethanol mixture, our oxidizer is nitrous oxide, basically laughing gas, and our pressurant is helium. This rocket also features a new payload for us this year. It is a self-controlled fixed-wing drone that will deploy from the nose cone at apogee and fly down to the ground. And as Christina said, we are competing in the $1 per foot challenge, which is different from the Spaceport America Cup that we competed in previously. Moving on, a little bit about our recovery system. We use a two-stage recovery system, meaning that first we have a drogue parachute and then another parachute much bigger than that deploys afterwards. You can see up in the top right a little bit of this parachute stage separator, which is fun and explosive. And all of the structural components on the rocket are made of carbon fiber, fiberglass, and aluminum. And another quick thing that I want to touch on before we get into sub-team acknowledgments is that another really big part of this rocket is testing. So part of that you see with the recovery there in the top right. But another big part of that is the static fires of our engine. So we perform our static fires at Menzel Lake Gravel, which is one of our top tier sponsors. And this is really important for us to test the reliability of our actual rocket engine. So currently we have gone there multiple days and have completed setups and also have completed pressure checks of up to 700 psi for the rocket itself and up to 1000 psi for our remote fill stand, which we will be talking about later. A couple weeks ago when we went up, we experienced some odd venting issues, but we have been working through them and we are still conducting testing, and our next attempt will actually be this Thursday and Friday. So please keep up to date with our social media and we will be posting how those go. So real quickly, even though this year has been really difficult, this rocket has been in the works since 2019, but there has been a lot of accomplishments. So you might have noticed on the first slide that it said 2019 to 2021. That is because this rocket was started in the fall of 2019, and then when COVID sort of kicked off in Washington in March of 2020, we quickly had a transition to online and then have slowly been ramping up back to in-person over the past school year. So the team has been working through a lot for the 2020-2021 season, but some big accomplishments have been finishing the design of Pacific Impulse, where they were left off in March of 2020. We've also concluded manufacturing of all relevant systems needed for launch and are also manufacturing R&D projects that could potentially be integrated later in the future. And we've had really successful integration between sub-teams. Again, I want to highlight the integration that's been happening between Propulsion and Avionics at those static fires, which you'll be able to see a little bit of later on. And also, all of these technical achievements are even more highlighted based on the fact that we've had to remain flexible within the COVID-19 environment and work within all university, state, and federal mandates, which we have done very successfully and have kept ourselves and the team at large and our community safe. So with that, let's get into the technical stuff and start highlighting our members. I'm going to hand it off to Zach Gomi, our structure sub-team lead.
All right, hello everyone. My name is Zach Gomi. I had the honor and pleasure to represent SARP as the structures sub-team lead this year. So getting right into it, as Kat mentioned, it was most definitely a difficult year. There's many challenges starting off. We weren't even sure if we were going to get into the manufacturer shops early on in the year. But I'm extremely proud of my team and every member in it, sticking to their guns, working extremely hard to get this rocket built. And so I'm extremely proud to express this through each project. Starting off though with structures, we are in charge of designing and manufacturing all structural and aerodynamic components on the rocket, as well as overseeing the recovery systems. Essentially, if you can see it on the rocket when it's fully built, it's probably structures. With that, a little overview, there are 8 different projects that our structures is composed of, starting off with nose cone at the top, all the way down to fins at the bottom. Intermixed, there's the payload coupler, the recovery coupler, and the airframes. And then the recovery systems I mentioned are essentially the parachutes, the nose cone ejection, and the parachute stage separator, all housed in that upper body tube there. So starting off with those projects, I'll start with nose cone. And speaking a little to the fact that everyone did extremely well, I would like to highlight everyone's names in each project. So the project lead for nose cone was Brandon Scheer. The project members were Alex Vasquez, Ben Huseric, Ignacio Ray, Karina Bridgman, Kyle Scher, Vivian Huyn, William Hines, and Ying Kwong. And the incoming lead for next year is Ying Kwong. The overall goal for this project was to manufacture a 47-inch fiberglass nose cone. So an extremely tall nose cone. It was a really tall order, but every single one of them did an amazing job manufacturing this, going through all the difficulties from previous years, and fixing them, and in a very short time span, manufacturing this extremely beautiful nose cone that I'm very happy to show off in the next little bit. And as I mentioned, the nose cone is manufactured and it is ready for flight. Next up is the payload coupler, one of our 2 aluminum coupler systems on the rocket. This project was led up by Alex Holden. The project members are Jacob Price, Eamon Haugen, and Trevor Akiningok. And the incoming lead for next year is Trevor. So the goals for this project this year was to go a little bit different than in previous years. In previous years, there were multiple parts that were welded together, but as you can imagine, that added extra time, extra weight for the weld, and an extra cost to actually weld the coupler. And so the goal this year was to make it out of a single piece of aluminum, which was extremely ambitious, but Alex Holden stayed true to his guns and developed a plan with his members and successfully manufactured a unibody coupler. So I'm extremely proud of them, and they paved a way for new coupler manufacturing in the future. Next up, this is the second of our coupler systems, the recovery coupler, led up by Greg Boyce. The project members are Aidan Vandenberg, Lucas Lesninkov, Nicholas Toyoma, Tyler Holloway, and Vincent Zhao. And Aidan will be leading it up next year. So this is more traditional of our coupler systems in the past, where we did have multiple pieces welded together. Greg and his team did an amazing job manufacturing each of those components, the cage, the bulkhead, and a couple sleeves, got them welded and also integrated in time. It is an extremely tall order because there's many pieces that had to fit together with very high tolerances, but they did an amazing job getting that done, and it is manufactured, tested, and ready for flight. Next up, we have airframes. There are many airframes on this rocket, as it is a long rocket and each little bay and tank has to be shrouded over. So Toby Moreno led this project up, and his members were Ashlyn McFarland, Isabella Carpenter, Jay Lee, Joseph Noth, Josh Ureda, Salma Hassanin, and Sean Earing Berry. And Ashlyn will be leading up the project next year. The goals for this project were essentially to manufacture each of these body tubes, which again is an extremely tall order because we have a little over 20 feet of rocket and every single part of it has to be shrouded over. So that means a lot of carbon fiber, a lot of fiberglass, and many hours in the composite shop. But Toby and his team did an amazing job getting that done, spending many late nights in the composite shop to provide an outer shroud for the rocket and a consistent outer diameter. And all airframes are in fact complete and ready for flight. Next up is the last structural component that you'll see on the outside of the rocket, and that is the fins. So Patrick Follis led up this project. His project members are Alex Vass, Alexander Unguez, Helen Carson, Patrick Ray, and Takahiro Soeda. And Patrick will be leading up this project next year. The goals for this project were to manufacture the fins and the fin can out of carbon fiber. Now the fins have had some problems in the past couple years, especially with the fin edges. They have to be very sharp on the edge. It has been extremely difficult to get that really sharp edge out of carbon fiber. But Patrick and his team figured out this new method of resin casting the fin edges. It turned out extremely well. You'll see it in a little bit, but we're really happy with how the fins turn out. They did an amazing job, and they are in fact ready to fly. So really excited there. Now getting on to the recovery system, starting off with parachutes. Barrett Siltebo led up this project with Evan Peterson and Ramin Jarahain. The incoming lead is Evan. So essentially there's two main parachutes on the rocket. There is the drogue chute, which is a slightly smaller parachute that ejects around apogee, about the highest altitude that we reach, so as to slow it down to a steady velocity. Once that's reached and we're at a very specific altitude, we release our main parachute. That is a much bigger parachute that is meant to slow the rocket down to its landing velocity. Now these 2 parachutes were manufactured in-house. Barrett led the team in manufacturing both of these parachutes, including all of the rigging that has to mount the parachutes to the rocket. They did an amazing job. As you can see in the picture there, doing some testing in the lawn, making sure it does in fact produce some drag. They also conducted some wind tunnel testing and are planning on conducting some drop testing coming very soon. So they did an amazing job making those. They look awesome. All right, next up is the nose cone ejection. So this was led by Catherine Butler, and her members were Andrew Liang as well as Anushka Sirod. Anushka will be leading it up next year. And so essentially this project is meant to eject CO2 canisters and all of the CO2 within the canister into a pressurized vessel so that either the nose cone or the payload coupler can eject off the rocket. In the nose cone case, it's to eject the actual payload, and for the payload coupler, it's ejected so as to release the parachutes. So there's 2 different systems that need to be ejected off the rocket, and so multiple systems of the nose cone ejection Raptors is what they're called, to be implemented on the rocket. So Catherine and her team did an amazing job manufacturing these Raptors as well as testing them in many different scenarios and many different times to ensure that they are reliable and will work during flight. They have been tested, as I mentioned, multiple times very successfully, and so they are in fact ready for flight. Now the last project I will speak on today is the parachute stage separator led by Ash Srauka. The project members for PSS are Brett Azamalum, James Ott, and Taylor Phelps. The parachute stage separator is meant to, as I mentioned with the parachutes, the drogue switches to the main. And so the parachute stage separator is what actually switches between those 2 parachutes. It's a pretty complicated system using pyrotechnics to release a little carabiner-like quick link there, so as to release the drogue and let the main open. It's a really cool system. Ash and their team did an amazing job manufacturing multiple versions of these, as well as testing them profusely to make sure that they will work reliably in flight. And the devices are in fact manufactured, tested, and ready for flight. As was kind of mentioned, all of the structures components are in fact ready for flight, which again I'm extremely proud of my team for, because they worked so hard to get this done, especially in the difficult times that we're in. So amazing job to everyone. I'm extremely proud of you, and thank you all for listening to the Structures projects. With that, I will hand it over to Josh Sherbrooke with Avionics.
Thanks, Zach. Excuse me. My name is Josh Sherbrooke. I've had the privilege and punishment of leading Avionics this year, and it's been a good year. So overall, we own the electronics and software that manages filling propellant of the rocket, launching it, and then flight. Over the last year, we've had a few key goals that we've really tried to implement throughout our various projects. One of which is taking electronics that would have otherwise been connected together by wires and putting them on printed circuit boards. This is for reliability and ease of use. We also have been making a push to make more highly configurable software to fit the needs of a changing system. Similarly, the way we handle telemetry this year, we've been really pushing towards a unified, sort of consistent model for dealing with what data SARP produces. And then finally, we've been really pushing to make our systems more reliable, and then to have failure modes that don't kill us when they do inevitably happen. So, with that said, let's get into some system architecture. So on the rocket, Avionics has a main flight computer and a flight data computer. The flight data computer, owned by Flight Data, gathers sensor data and logs it and then forwards it to the MFC to be sent to ground control. Then on the ground we have a propulsion controller and a fill controller, which manage respectively the propulsion systems on the rocket via a quick disconnect plug and our fill stand. And then on the other side, far away where we're all safe, is our ground control system, and I'll elaborate on those things more soon. So our first project is launch operations, led by Ryan Hallgrimson, with heroic work from Matthew He and Tim Manziuk. Launch Ops, over the past couple of years, has developed a generic printed circuit board to output power and receive sensor data input. And the idea here is that by having sort of this generic architecture, Launch Ops is able to adapt for a given year and a given configuration what this system does and how it manages things in a redundant and safe way. But really, I think these folks have a lot to be proud of. Architecturally, this has been a really important system for avionics, so big kudos to them. Next up, we have the flight data team led by Craig Robertson with Braden Gomi and Lahari Nidadavulu. Flight data is on the rocket, as I mentioned. It gathers sensor data, logs it, sends it to the main flight computer, and then that is disseminated to our ground control systems. The idea here is that we want to get high fidelity data from our rocket. We want to have an understanding of what's going on and good engineering data for what's actually happened during flight. You can see we have a printed circuit board that sits in the rocket populated with mainly off-the-shelf components, which has been a great mix of having everything consolidated and being easy to use and implement. So great job to this team. Next up, we have our networks and communications team led by Nick Monsees with Iad, Noah, and Larry. Netcom is really the glue that holds avionics together. They manage our 2.4 gigahertz long-range Wi-Fi network. So in order to keep us at a safe distance so that rapid deconstruction of our rocket doesn't mean rapid deconstruction of us, we have a very long-range Wi-Fi network that they manage. We also have a 900 megahertz radio connection so that we can communicate with the rocket in flight that they manage. They also have implemented onboard live streaming so we can get camera live video streams in flight, and then pad cams, which give us a lot better understanding of what's going on when we're remotely managing and filling the rocket. So great job to everybody on that team. I'd like to also thank Nick in particular. He's worn many different hats on SARP. He was my boss last year, and now the tables have turned, but thank you very much, Nick. Next up, we have ground control. So after we get all kinds of data from different dispersed controllers, it needs to come to some central place. So Jason Chen led this project with Jessica Burrows and some contribution from me as well. And when data comes in, we have a first layer of software that collects everything from different controllers, puts it together into one state of where SARP's rocket is at. And then we have a variety of different telemetry subscribers that we use to visualize data that comes in and to send commands to the rocket. And overall, I can't overemphasize the importance of having this unified ground control system that sort of interacts in a clear and consistent manner with all the different systems on SARP, because as the rocket gets more complex, avionics does too. And the work put in by ground control to have a really good foundation for our architecture of how things talk to each other has been very meaningful this year. Next up, we have testbed led by Jeffrey Gao. And as sort of to follow our goal of increasing our system reliability, we have placed emphasis on testing our software and testing our electronics. One side of that has been continuous integration and continuous deployment of code that he's worked on getting spooled up for our GitLab repositories, which we are going to be using moving forward to make sure that everything works when we are committing it and when we're putting it onto our controllers. And then he's also done some great work on getting a hardware-in-the-loop system so that we can test our controllers, our electronics, in an integrated fashion in a flight-like way. So this is going to be really exciting moving forward. And again, as our complexity increases, this is going to allow us to continue to produce reliable systems. And then our last project is the Autonomous Recovery Experimental System, or ARES, led by Avionics with Alyssa Weed, Luke Salah, Nico Miguel, and Nathan Yan. This is a almost mind-numbingly difficult project. The goal is to, instead of letting the rocket fall where it likes under parachute, to steer with a parawing the rocket back to a predetermined landing zone. And essentially the problem is one of controls. How can you move this thing falling under parachute and keep it on a track? They've done a huge amount of great work here. We have most of our hardware is complete, and we're moving forward into subscale testing, and then we hope to fly the full-scale system next year. So great work to that team. And somehow this slide got taken off, but I'd like to also thank Chris Yu for his work with electronics integration. He's been sort of the glue towards my software expertise, and he's been really focusing on all the electronic side of things and has been filling in the gaps wherever there's expertise and help needed. So thanks, Chris. With that said, I will hand it over to Oliver Ruo with Propulsion. Thank you.
All right, thank you, Josh. Great job to the Avionics team. So my name's Oliver Rowe, and I'm the propulsion lead for this team. Propulsion definitely had a lot of difficulties this year, given the fact that our system moved from a hybrid system to a bipropellant system, essentially meaning that we have 3 times the amount of tanks and about 10 times the amount of plumbing that needs to go into the system now. So really happy with what the team has been able to put together this year, and yeah, let's get into it. So propulsion, arguably the most exciting and important part of the rocket, according to our Professor Hermanson, our advisor. We also spend the most amount of money, so that also says something. But we are in charge of designing and manufacturing the propulsion, all propulsion-related components on the rocket. And this can range kind of in main parts from the remote filling system, onboard fluid management, the rocket engine design, and then also engine testing. So this picture is not to scale, unfortunately, but we have kind of various tanks on board: the oxidizer tank, fuel tank, pressurant tank. In between those tanks, we have various bays that house plumbing to run all our propellants down to the combustion chamber at the bottom. And then we have a couple projects off system, being ground ops and the remote fill system. So in terms of our projects, Middle Tanks was led by Hong Nam Van this year, with project members Ali Balou, Alejandro Martinvilla, and then Evan Lapp. Middle Tanks had a really interesting time this year. We produced some tanks and went to get them tested at hydrostatic testing, and unfortunately some of our welds failed due to faulty welding. And then we tried again, and then we had some more issues, and so we had to end up remanufacturing our tanks in about the span of a week. And thankfully we did it, thanks to like a ton of hard work and a lot of late hours by the team. But fortunately we did remanufacture our tanks. They look great and they work great. So kind of the goals of the project, of course, are to make tanks to house for fuel and oxidizer up to pressures of about 950 psi. And we were basically able to accomplish that this year after much trial and error. Another project that we had was composite overwrapped pressure vessels, led by Josh Forsyth with project members Megan Clemens and Danny Nankova. The project will be led by Danny next year. In terms of goals of the project, they were mainly to design and manufacture COPV tanks. This year we weren't able to fully manufacture tanks for use. That will be done next year. But we were able to create a new tank design through a lot of work from Josh, doing some coding on MATLAB and some CLT code, which I don't really understand. But we were able to do some skirt winds over our COTS pressurant tank, which you can see in that picture, and which was really cool to see. The X-Winder has been very finicky. It's basically our winding machine. But yeah, great work to that team this year. The next project is actuated valve bay structures, led by Parman Kaur, with project members Adrian Lowe, Aidan Vandenberg, and Anna Yates. The next lead for next year will be Alejandro, who was on Middle Tanks this year. The goals of this project were to essentially manufacture all the structural components for the bays. This included pillars and then interface rings between the tanks and the pillars. And the point of this is to essentially not transfer any loads that the rocket is exerting onto any plumbing. So as the rocket goes up, you get G loads, which compresses everything, and you don't want your plumbing to compress because that might break. So we want to have structural components there to take that load. And fortunately, we were able to basically manufacture all the structural components successfully, and the team did a great job overall. So good job to them. Next project is System Interconnects, led by Malcolm Jackson, with project members Khalil Jones, Aidan Vandenberg, Catherine Wilborn, Cedric Nagata, and Parman Kaur. Next year's lead will be Khalil. The goals of this project were to design, manufacture, and assemble all onboard plumbing along with the valve actuation mechanisms. Really big project. As I mentioned earlier, there's about 10 times the amount of plumbing compared to previous years. And that all has to fit on this massive rocket in between all the tanks. The valve actuation has double the valves, 1 to 2, which does also complicate things, makes it very tight, small spaces to work with, but the system is essentially all put together. Everything is on there, everything was manufactured, and we tested the system up to about 1,000 psi, and it's performed pretty well thus far. So we'll be working with this more as we go into hot fires this week and in the future, but exciting stuff from this team too. Next project is Thrust Chamber Assembly, led by Danilo Sandersky. Project members including Benjamin Wawsa, Chris Vandenheuvel, Grace Zalpi, Michelle Graebner, Ryan Myers, and Anna Yates. So, Thrust Chamber, essentially manufacturing the rocket engine, of course, which includes the injector, combustion chamber, TPS, and nozzle, TPS being thermal protection system. This year we were able to accomplish that. We've manufactured our pintle injector, combustion chamber, nozzle, and one set of TPS that we've been waiting to test. So hopefully that'll happen this next week. But yeah, great job to this team. Next team, which is a team we decided to add this year after much consultation with previous year's leads, was Ignition, led by Josh Walcher, with project members Hee-Jung Lee, Michael Gabales, Mitsuki Shimamura, and Thurston Duong. Next year, the project will be led by Michael. So Ignition had quite a few goals, but the main one was to create a reliable pyrotechnic igniter manufacturing process. And then along the side, we designed an arc igniter R&D along with a torch igniter. But this year, they were able to successfully kind of fine-tune our pyrotechnic igniter production methods and also test those. They're working great, about 10-second burn time, very energetic. But the arc igniter is kind of their focus now that they've finished the pyrotechnic, and hopefully they're looking to possibly implement that onto an actual rocket on board ignition in the future years. So a lot of exciting stuff that this team will be doing in the future years, and I'm looking forward to seeing where it goes. And then remote fill, led by Isfar Nugulaswaran, project members being Ian Minotani, Connor Stroop, and Jamie Shah. Connor will be leading this team next year. Remote fill, arguably one of the biggest money spenders on the team. Got a lot of big ball valves on there, a lot of plumbing, really high pressures, but really cool project. Goal is to basically fill the rocket with nitrous oxide and helium from about 20 feet away. It is controlled by Avionics, but we do all the mechanisms and all the plumbing. And it was a pretty much a completely successful project. They finished up assembling the system very early, helped out a ton later with other projects, so big shout out to them. But we've been able to assemble and test the system up to about 1,000 psi out in the field, and it's been working great. So looking forward to working with this more and seeing where it goes in the future. Next we have Ground Ops, led by Harrison Robel and Gabrielle Sprunk. Two-man team working on a really big project, did a great job. Basically their goal was to assist in test fire operations by creating a static test stand to strap the rocket to, since we don't want it to fly away while we're trying to test the engine. And then also they were in charge of designing and manufacturing a new launch rail. This year they were able to fully complete the test stand, and we'll be able to attach the rocket to it. It's been working great so far, and we'll be using it more into the future as we continue to test. The launch rail will be manufactured next year, along with another R&D project on this team being a horizontal test stand for just motor tests without a full stack, so that'll be really exciting to see as we move into next year. And our final project is regeneratively cooling R&D, led by Quentin Roberts, project members being Ryan McCluskey, Jared Smythe, and David Men. Regen will become a much larger team in the future, given the fact that we are trying to move a lot of our engine design into a regen-cooled system. So incoming leads will be quite a few, including David Men, Danilo Sandersky, Grace Zalpi, and Anna Yates. The goal of this project was to design, manufacture, and test a regeneratively cooled engine. And this year we were able to get through the first iteration of design and begin the manufacturing process, as you can see in the pictures. But regen is notoriously hard to design in itself, given the fact that a lot of the analysis isn't always accurate, and you need to find a lot of unknowns through testing. So this project will be flushed out greatly in the next year, and I'm really excited to see where it goes and how it turns out, because this will be a really big part in what we want to do in the future. And with that, I will be handing it off to Akash to do Payload.
Good evening, everyone. I'm just going over the Payload's progress this year, which has been significant and impressive. So this year we were responsible for designing and developing a ejectable drone from the main rocket, and as you can see, we are situated in our nose cone. And in order to accomplish this challenge, we broke our system down into three main projects: electronics, controls, and structures. You can see electronics and controls, or electronics and structures are represented here, but I don't really know how to represent code without making it look like a cheesy 90s infomercial, so let's get into it. So electronics was led by Alex Velazzi, and the project members were Owen Lister, Esther Sohn, and Alex Jolly, with the incoming lead being Owen Lister for next year. The goal of this project was to design a novel control board and control system for electronic control system for the entire drone, which we were able to accomplish with really no major issues or hiccups, which was something we were really proud of, because this is the first major PCB we've designed on Payload. And this brings us to controls, which was run by Chris Phan, and the project members were Lexi Chow, Kayla Hong, Kelvin Wynn, Tim Wu, and Trevor Garode. So the purpose of this project was to design and develop a control system for a deployable UAV, which we were also able to do. We were able to design all the simulation, deployment, recovery, as well as integrating most of the sensors into the drone. The only thing we really have left is a couple of kinks we need to figure out with our control system and integrating it with our hardware, but overall it was a very solid and well done job, so it was super exciting for us to be able to have that progress this year. Finally, we have our structures team, which was led by Sydney Brugman, who will be next year's payload lead as well. And the project members were Gabe Earth, John Shanafelt, Ben Fredders, and Andrew Newman. And the goals of this project were to design a novel mechanical structure for the entire drone, including a deployment system and a method of integrating it with the rest of the rocket. To our great pleasure, we were able to figure out a wind tunnel model. We were able to design and develop an attachment system to the rest of the rocket, as well as a deployment system from the rest of the rocket. And we were able to finish pretty much everything but the wing folding mechanism, which still needs a little bit of prototyping and design in order to be integrated as a complete design. All in all, I would say this year was a massive success for us, and I wish Sydney Brugman the best of luck for the future years. And that brings us to our business sub-team with Vandana Manoj.
Alright, hi everyone. My name is Vandana. I will be next year's business sub-team lead. And I'm really excited to talk about all the things that we've accomplished on the business team this year. So here are the members that have really contributed to all of our accomplishments this year. Donna Coyle, Gabrielle Sprunk, Paris Singh, Andrew Newman, Josh Welcher, Sally Yoon, and Aiden Vandenberg. And our incoming project leads will be Gabrielle Sprunk on design, Paris Singh on corporate sponsorship, and Sally Yoon on social media and outreach. And some of our accomplishments this year include establishing our corporate partnership program, launching our SARP merchandise and the Pacific Impulse mission patch, and hosting some membership events to build team community. So our partnership program, the focus of it is to build long-term mutually beneficial relationships with industry leaders. So some of our partnership opportunities include brown bag information lunches, mentorship, workshops, and recruitment promotions and info sessions. And you can help by joining the partnership program. You can contact our corporate sponsorship lead, Paris. His email is on the screen. And some of our current partners that I would like to thank are Black Sky and Hermias. And another thing that we accomplished this year was our in terms of like administration and merchandise, we have this is what our shirt looks like this year, as well as our mission patch. So we have the merch order form that will be linked in the live stream chat. If you would like to place an order, those will be due by tonight. And now I would like to present and thank the sponsors of SARP for all their help and support this year. It really means a lot to us. So first, in our purple tier, the Kirsten Wind Tunnel and Menzel Lake Gravel, ANSYS, Systema Technologies, HeatCon, SolidWorks, and Torre. Thank you all so much for all your help and support this year. And then on our platinum tier, we have Airtech International, and then the gold tier, Northwind Composites and the Velocity family. And then here we have our silver tier, Lauren Den Herder, Sherry Bronstein, the Hallgrimson family, the Durkee family, the Monsees family, the Holden family, the Smythe family, and Pacific Metallurgical Inc., All Wire Electrical, and Janicki Industries. And then here are our bronze tier sponsors, Renee Dockweiler, Online Metals, Dwight Newberg, Gerald Berg, Carly Breaker, Tracy Hines, Jimmy Reagan, Amy Lowe, Christina Dong, Norris Vandenberg, Jess Grant, Margaret Gintoli, Jared Houghton, Kevin Chow, Greg Cheadle, and Alexandra Abeta, Paradigm Structural Engineers Incorporated, Zachary Perry, Alexis Haroon, and Lucas Heflin, and the Olson family. Thank you all so much for your support. And with that, I will hand it off to Josh to do some senior acknowledgments. Thank you.
So due to COVID, we've developed Specific Impulse over the course of 2 years, which means first I'd like to take a moment to thank and acknowledge the graduating class of 2020. These folks put in a tremendous amount of blood, sweat, and tears into creating the foundation for a rocket that they didn't get to see launch. But we wouldn't be anywhere close to where we are today without their work. So thank you so much to the graduating class of 2020. And next, I'd like to give a send-off to the graduating class of 2021 this year. So much work, grit, late nights, and early mornings has gone into the creation of Pacific Impulse, and I think we're left in a very good position by the graduating class this year. So thank you for all your work.
All right, and with that, we are really excited to show off the physical rocket, but right before we do that, we're going to show you guys a short film to show you all the hard work that went into it. I didn't mean to take that. Alright, welcome back everybody. So as you can see, we have our rocket here and we are so excited to unveil it for you all. So, okay, on go, alright? So 5, 4, 3, 2, 1. Alright, here it is. This is Pacific Impulse, our first ever bipropellant rocket. It's, what is it, 21 feet long?
21.
3 tanks, lots of plumbing, a lot of hours. Okay, so Josh, do you want to come join me real quick? Okay, awesome. So we want to just reiterate, we are so thankful for everyone's support, all the family members, all the friends, all the sponsors, any industry mentorship that we have received. We are incredibly thankful for all of it. This rocket will be launching in fall 2021. And so now I'm officially going to sign off as Chief Engineer of this year, and I'm going to hand it over to my successor, Josh Sherbrook.
Thank you, Kat.
Yeah, man.
All right, we'll take just a moment to look forwards towards next year. So I will be the chief engineer. Catherine Butler will be our project manager. We are introducing the position, the profoundly important position of manufacturing lead, co-led by Alex Holden and Ash Shirauka. Ani Yates will be our secretary. Vandana Manoj will be our business lead. Ryan Holgrimson will be leading avionics. Patrick Follis will be taking structures. Sydney Brugman will be our payload lead, and Josh Welcher will be leading propulsion. So big year ahead of us, and before we move on to Q&A, I'd like to discuss one more thing looking forward. So we at the Society for Advanced Rocket Propulsion have spent much of our copious spare time thinking about what we can do to make our society more advanced. And I think that really the question is, after we fly a liquid bipropellant rocket, what is next? And I'm very excited to announce the answer to that question is space by 2025. UW now has a space program, and that's us. So looking forward into the next year, our goal after we launch Pacific Impulse is going to be to bite off the biggest chunk of technical change towards what we need towards space that we can, while still making something that we can launch again. Next year we're going to be seeing a lot of work on developing a regeneratively cooled bipropellant engine, restructuring our engine test paradigms so that we can get high volume engine testing instead of doing fully integrated tests, investigation into active guidance, increasing our outer diameter of our rocket, putting more composites on the rocket, and ultimately this all comes as a result of support from sponsors like you. So thank you to our sponsors, to our team, to our leads, to our parents, to everybody who's made this happen, and thank you for coming. Now we'll move into our Q&A over Zoom, which is linked in the description for this video and I believe in the chat as well. So if you'd like to learn more about this rocket, more about SARP, or just come and talk to us, we'll see you over on Zoom. Thanks so much.